Where is Tübingen? This is first question. It is in Germany, so this is a map of Germany, and Tübingen is in the southwest. So here you see probably a small well-known, it's very close to Stuttgart. This is where the good cars come from. So you see this in Porsche and so on. But here, a minor place compared to Stuttgart. But it is one of 11 German excellence universities. It has about the size of Visoda, so we have 90,000 inhabitants and 28,000 students. It's very famous for its picturesque old town and its intellectual history. So we have this year, in the coming year, we have the 550th anniversary of the university. So, and also, it is not Oxford who invented punting, that's actually Tübingen. So we have these punting boats here on the Neckar River, and it is a very old tradition here. Okay, my main research interest is in classical many-body systems. I started out actually in quantum field theory. I did my doctorate there, and then later on switched to what I would call liquid state theory. And according to Landau, it is a very hard problem because you don't have a small parameter in liquids. And this is already manifested in the pair correlation function. So this is quite well known. So this is a typical liquid state pair correlation function. It's the probability to find a second particle at a certain distance from the first particle. And it has these strong oscillations due to layering. And it's actually not easy to have quantitative theories about that. So then, in my group, we also do experiments. And we experiment usually with colloids of the size of 1 micrometer. So these colloids you can see in the microscope. This is the advantage. And so you see all the phases of matter with the microscope under particle, single particle resolution. So this is plastic, essentially plastic balls. But the advanced piece of equipment is the confocal microscope. With that, you get the full 3D image. That. So what is particularly interesting for me, okay, so you have a 3D image, and then this is a crystallite drawing. And you can track the neighborhood of each particle, and you can see whether it is in an FCC environment or exactly close back or whatever. Yeah? So here these different colors, they assign different crystalline structures. So blue is liquid, I think red is hexagonally packed, and green is, I think, FCC. And what I do is, I study these crystals with classical density functional theory. This is the poor sister of quantum DFT. So quantum DFT is used by so many people, and actually people don't know that there's also a classical variant of it. And this is my main topic of research these days, so I try to make it very quantitative with machine learning methods, but this won't be the topic of my talk today. What you need in classical many-body system is sort of a ground truth, and this ground truth is then provided by simulations, and this is what I will tell you later on. So the final slide of the presentation of myself is why am I here in the first place? So there is a joint project now running since about 4 years between Brazilian and German places, well, as the German place is Tübingen, and this is financed by the German Academic Exchange Service in Capes on the Brazilian side, and it is about modeling fields. And this is what Ismail is known here for, and that's why I'm here for the first time, and but we've been already collaborating for longer, for 3 years now. The project is headed by Professor Fabio Reich from the Universidade Federal Fluminense in Niterói, And on the German side, there's also my colleague Frank Schreiber, who's heading a very big experimental lab, where on the one hand they are doing organic molecular beam deposition of these thin films, and these tend to be quite complicated, and we are trying to develop very simple models for that, actually. Okay, so with that, I would like to start. So this is the outline of the lecture. First question, why simulate at all? I gave you already a reason, sort of the ground truth. It is supposed also to bridge experiment and theory. And then I go into several methods. The first method is a very obvious one. It's molecular dynamics. You take particles and you say, I don't know anything about physics except Newton's laws. Then let's simulate Newton's laws. That's it. You can do this, but there are also other methods. So if you want to do this in atomic resolution, you soon enter borders and boundaries. And so the question is, can you simplify things? Can you coarse-grain your models? This is the chapter 3. And then you see also how you get from, say, electrons and quantum systems to colloids. So these 1 micrometer plastic balls that I've described. So section 4 is then on Monte Carlo methods. So it is a special method designed to treat thermally equilibrated systems. And this is not performing an actual dynamics, but it's throwing dice. Hence the name Monte Carlo from the casino. And in the course I try to give a few illustrative examples on these methods. So why simulate? As I said, I want to bridge experiment and simulation. In experiment, you're often hampered by resolution. You can measure very often only macroscopic observables. Experiments on estimate are costly, time-consuming, and in general, you cannot access all degrees of freedom. And with that, you would like to have a microscopic representation of the experimental system. You have full detail, you have access to any observable, and you can control many parameters. And if you have enough time and enough computer power, you can also sweep across all these parameters. But in all of this, it should be joined by theory, I think. So we have analytic models because they give us the insight, they give us trends, they form the understanding for us. And I would say experiment simulation and theory, they form a magic triangle of physics these days. Okay, if we talk about simulation methods in nanoscience, we should talk about length and time scales a bit. So in the length scales I'm concerned about, they range like from atomic scales, so this would be a few angstroms, up to a few micrometers, and this is typically the end of the colloidal scale. And this is where you employ these methods, so all atom is of course limited to a few tens to 100 nanometers, and accordingly also the times go up to microseconds, and then it's the end. Therefore, you have to coarse-grain the models in order to go to, say, milliseconds. Milliseconds are the time scales, very interesting for biological systems and also for actual material science. But material science that invented more these continuum methods that I won't talk about, which can go up to seconds, minutes, and hours, and so on. Yeah, Monte Carlo as an equilibrium method has no time scale, but it spans so basically the whole atomistic colloidal scale. Okay, so first, molecular dynamics. As I said, easy. Huh? So, take n particles. What do you need to do? You specify positions and, is it enough? No. But that's the velocities. Huh? Yes. Newton's equations are second order, you need positions, velocity. You start with that, you compute the forces, and then you integrate the equations of motions. Maybe you have tried this in one of your undergrad courses, so with a simple, one calls it Euler time step scheme, and it fails. So I don't know whether you've tried to predict the motion of the Earth around the Sun, and you do it with this simple scheme, and like after half an orbit you're off. So that's why you have to work a bit harder. So there are these clever methods called Rayleigh, leapfrog, or velocity Rayleigh, where you have to do a sort of semi-implicit scheme, treating positions and velocity slightly differently. And then it works, I would say. But still, small time steps are needed in order to do this. And this limits the range or the total time, physical time of simulations. So how do you get then reasonable observables? Yeah, this is clear, this is always a time average. You would have the assumption any measurement process is, for a reasonable experiment, is a time average. And well, if you're in an equilibrium system, then you have the harmonic theorem, and then you also have a statistical average at the same time. Now, if you have a non-equilibrium system, things get difficult. Okay, let's talk about atomistic systems. It's actually more a domain of chemistry, I would say, by now. But what you would like to do is you have complicated molecules, and you want to predict their motion, and also their internal motion. How do you do this, actually, classically? It is also quite simple-minded, and here this is the example of CO2, carbon dioxide, which is a linear molecule. And how do you parameterize this? Then, of course, actually the point masses that move are the C atom and the O atoms. And then you have internal motion of the molecule. That is bond stretching and this is wiggling. And so this bond stretch is usually a harmonic potential. And with that you have the internal interactions. And then you worry about the interaction of two of these molecules and how do they interact. This is also quite general. Everything in matter is about van der Waals and electrostatics. That's it. There's nothing more. The van der Waals interaction are a universal attractive strength which exists between all neutral atoms, essentially. And its origin is fluctuations of the electromagnetic field, so it's a quantum effect, actually. And this has to be added on top of explicit electrostatic interactions. And here we replace complicated chemistry by so-called partial charges on the atoms. So these partial charges reflect the polarization of the molecule if you want. But then you use standard interactions, Coulomb interactions that you know from physics 1 or 2. Again, so methods are intricate in order to do this right, especially to avoid finite size effects. So, and by now this is actually well developed. There are called as force fields for all different sorts of material classes, and they are integrated into big simulation packages. And these you can use. The only thing is you should ask the internet actually what these force fields are good for and what they have been designed for. Otherwise, you simulate something for which we have not been designed. And here is an example how such a simulation looks like. This is really a cartoon. But then there's a CO2 flies around, and so you get the orientation of the molecule, and you get positions and velocity. You can calculate the total energy in the system as a function of time, or say a mean square displacement between any two of the molecules, whatever you want. And then it's actually only a matter of harnessing large computer power. So, you might have thought, that's it, you can run this system simply as described. Suppose you have picked a good integrator for the equations of motion. And again, from physics 1, we would say this is ensemble, microcanonical, where you conserve the number of particles, the volume, and the total energy. It sounds very natural. Next problem is the energy will always blow up in your simulation. Now you cannot really conserve energy, therefore you have to add little tricks in order to conserve energy, and that actually makes that ensemble not very convenient. So the most convenient molecular dynamics ensemble is actually the canonical one, where you sort of fix the temperature in your system, at least if you can simulate at equal temperature. And this gives you a distribution of velocities in the system, and this is very well suited to calculate structural and dynamic properties. But sometimes you also need to take into account that the volume of your system can fluctuate, and this you can do in the isobaric ensemble NPT. So you can add actually arbitrary fluctuations of the simulation box size to the dynamics. It's very useful for simulating crystals, very useful for simulating chemical reactions, and you can also phase transitions there. A bit off is this red canonical thing. Red canonical means you fix a chemical potential and you don't have particle number conservation. This is strange. So how do you simulate something where particles can enter and leave the system? So this is a very modern strand of simulation science, I would say, where they bridge classical molecular dynamics with a grand canonical bath, I would say. Okay, if you go to non-equilibrium, things get more difficult. Whenever you want to simulate a genuinely non-equilibrium effect, you have no choice but do what I call here direct non-equilibrium molecular dynamics. It's very difficult because you have to decide what is the proper average actually. So you have probably an average over different initial conditions in the system, and this has to be chosen wisely. And here is an example where I say, okay, you want to calculate a typical transport coefficient, the viscosity of a liquid. You would say, okay, how do you do this? Well, in non-equilibrium, you could say, yeah, well, you explicitly create a flow situation. In this flow situation, you measure stresses or forces and you divide by shear rates. This is, again, what you would learn in fluid dynamics. And this is challenging. And therefore, people also have invented clever equilibrium methods where you can measure the same quantity viscosity from an equilibrium simulation, where you measure correlations between forces, and they give you access to transport coefficients. This is one example of the so-called Green-Hugo relations. So it's a cornerstone of non-equilibrium thermodynamics from the 1960s. So here I want to show you a particular explicit non-equilibrium ensemble from example from biology. It is about protein folding. It's still a considerable problem, even though we have now access to AlphaFold. And here a showcase is VIII. Do you know VIII? No, I have no idea before I entered this field. VIII is a small protein which sits at the intestinal epithelium. So you have your intestines, and then you have the border between the intestines and the the rest of the body, and somewhere there is sitting also this Berlin. And this Berlin has a headpiece, and this is here, so this is sitting here, and this is one of the fastest folding proteins that we know. It folds within a microsecond approximately. Right? And this is, by biology standards, really fast. So you have these processes on the millisecond to second time scale, and as I've told you, this is inaccessible to molecular dynamics. So here is also a cartoon. So the folded state of these headpiece would look like this half-open rectangle, more or less, and this is then connected to a certain biological function. Okay. And so this was the first protein which was then simulated directly in the 1990s, so it's about 30 years ago, and where they could directly show that molecular dynamics leads to the correctly folded state. That's why I showed you this example. Okay, and so the next thing is then a little video from this lab, from the Schulten group in the University of Illinois, who did the simulation first. Maybe I just find it. But I say a few words to it. So actually this simulation contains everything. It contains an all-atom representation of the protein, from which you only see a backbone representation, like the biologists do. So you really have to condense the output to a graphical representation. And of course, the system contains the whole cellular environment. So it contains explicit water, it contains explicit ions, which set the salt concentration in water, which is decisive in order to screen the electrostatic interactions of protein charges. And okay, I'll go back and show this again. So again, all of this is neglected in this little movie, and this little movie starts with the stretched conformation. So this is actually the final conformation it should reach. So the simulation starts with a stretched conformation, and now with let it go. And actually, it takes a while until it first finds an approximate shape, and from this approximate shape, it eventually finds the final shape. And this is also a rule in biology that you have these stepwise processes, and these stepwise processes are connected to free energy barriers. And these free energy barriers, you can measure them also with these simulations. You can measure these also with explicit single molecule experiments. And this is an example here. Still, you can find super important theorems in statistical physics, and this is one which has been found only recently. Recently means like about 20 years ago, 20 plus years ago. It is the so-called Jarzynski inequality, and it relates an average over the Boltzmann factor of the work you do in the non-equilibrium process to the change in free energy, where the initial and the final state are equilibrium states. Super important theorem. This is something on a non-equilibrium path. You stretch the protein, you fold the protein, and there's work associated with that. In the end, this is all related to the free energy barrier. Okay, this you can simulate, either explicitly, or by implicit methods where you just get the free energy difference between these states. Okay, all atom comes to limits, and this is now about coarse graining. And so we did all of that. I told you about this. Coarse fields exist, software exists. Coarse graining has become an industry. And essentially what you want to do is you want to go from nanoseconds to milliseconds, goal number one. And goal number two is you want to have many particles, many proteins. So you want to address cell assembly phase behavior, and large aggregates. So in the biological world, very well known is the T-force field, and it's the initial phase, of course, where you just lump together four atoms to one superatom, and you try to more or less parameterize the effective interactions between these superatoms. So you can go on with this, and I'll show you on the next slide. If you have more and more atoms into effective atoms, then you can improve your coarse grain scheme. And quite different actually from this like bottom-up coarse graining is what I would call colloidal simulation. Colloidal simulation starts from simple shapes altogether. So we start with spheres. Spheres are usually hard, since there is steric exclusion, usually between atoms, between effective proteins, between macromolecules, and so on. So everything is lumped into exclusion force, shape force, tropic force, and then you put charges on these. You put van der Waals interactions on these effective charges, and you simulate these systems. Yeah? And the connection between these two is not quite clear, what we say. Yeah? But this is then what we can also do experimentally with doing these colloids. If we want, we can produce such macroatoms with colloidal techniques, and then these simulations are also top on. Okay, but here's an example, again, from biology. So on the left-hand side, this is a lipid molecule, which is treated here by Martini force field. So a lipid molecule only consists of a few beads, and therefore you can simulate many of them. On the right-hand side, this is also a very active field of research on antibodies. So antibodies regulate the immune behavior in your body. And this is the future of immune therapies. These antibodies, these are these molecules with like free lobes. And these lobes, they have active sites which address foreign and poisonous things in your body. And so what the biochemist engineer is actually is the head group, which addresses a certain virus or whatever, and then it's up to the pharmacologist or even the physicist to put that stuff into your body, and that's not easy, because if you prepare a high density solution of these antibodies, that stuff won't flow. So you have sort of a gelish paste, and if you try to inject it into your body, all what you produce is a lump of gel under your skin, and you have no protection. So it is of interest to design the viscosity of these antibody solutions, and physicists have played with all sorts of resolutions in treating these antibodies. So we also took part in this business a little bit. We investigated mixtures of these immunoglobulin antibodies with another widespread protein called bovine serum albumin. This is found in cattle. This is from cattle bovine. Also, the human version exists. Function is not important here. This is a physics protein. It is a very globular one. It is very stable. You can treat it almost as a sphere, almost. And so we looked at mixtures of those. We tried to see whether mixtures improve the flow properties of these. And then we needed to develop also the coarse grain model of this one. And how do you do this? I described this briefly to you. So you actually take an all-atom representation of the system, and then you identify the biological domains. And domains and proteins are those sequences of carbons which are found also in other proteins, so kind of which developed independently, but then were stuck or put together by evolution for other functions. And it makes sense to put effective beads on these domains. And by that, bovine ceremony becomes a 6-bead particle, and this particle needs to parameterize the interactions, like you have torsional angle flexibility, you have the so-called dihedral plane flexibility, and with that you get a full coarse-grained force fields with that. But how do you get the actual potential parameters from that? Yeah, actually for that you perform all atom reference simulations. So this is a picture done here, and you track the centers of your domains, and then you put histograms of, say, for instance, a bond distance between any two atoms, and then you try to fit in the end to the Gaussian, and from the Gaussian you extract potential parameters. So this can be done very reliably, and with that you get actually quite reliable, effective coarse-grained model for your protein. What can you do with that? So here's an example. Okay, as I told you, flow is very important in these systems, and the prerequisite to flow is to study diffusion. So the random walks of these particles in their own solution. And this is a strong function of the volume packing fraction in the system, and in the biological systems, you're around here. 30 to 40%. So it is actually your cell is quite a crowded place. It's not the representation from your bio textbooks from grade 6 or 7, where you have a few things floating around, but it's actually fully packed. Fully packed of proteins, fully packed of stuff. And this makes it slow. And here we show the translational diffusion coefficient normalized by the one at low concentration, and one sees, let's go look first at experimental data here. These experimental data, they drop from say 1 to about 5%. So the actual diffusion goes down by a factor of 20 in the cell. And so this is for this PSA, this is for antibody, and then we try to model these things also, and then we see two main effects. The first effect we call the Brownian effect. So perhaps you know